Okay, acid bases and equilibrium. The first thing is, what is acid? Okay, the definition of acid. So it was Arrhenius. Now acid is known for a long time in human civilization, and the term acid basically comes from the from the Latin word acidus, means sour. Okay, so it is Arrhenius in 1887. He tried to define acids more scientifically. Now, when you say sour, now anything that is sour is not always an acid. So it's not a very scientific way of saying. So Arrhenius defined acid as those substances that can produce H plus ions when dissolved in water. Okay. Uh, Now it remained like that for quite some time. And as you can see, the problem is it is water based, and H plus ion is a proton. Okay, if you think of what H plus ion is just a free proton. So free proton cannot exist in nature was a big question. Okay, but it worked for all purposes. We worked with it, but later other definitions came in to make it more robust, more inclusive of other compounds. Okay, and also took away the uh, presence of water. So you can now define acids in absence of water. So that is the Lowry and Bornstead definition. So when you look at Arrhenius definition, remember that it defines acid as substances that produce H plus ions. So these are the keywords: produce H plus ions when dissolved in water. And that's why HCl, which is a gas actually, okay, it can it is an acid when dissolved in water because it can produce H plus ions. Now naming acids. So, and these are some of the common names that will come across. So when an acid dissolves in water, it produces a hydrogen ion and a simple non-metal anion. So a prefix hydro is used before the name of the non-metal, and the "ide" ending is changed to the ic acid. So if it produces simple non-metallic anion, simple non-metals means chloride, bromide. So these are simple nonmetals. You get them from the periodic table. Okay, so you put the name hydro in front, and then ic acid. So that becomes hydrochloric acid. So HCl becomes hydrochloric acid. Now, if it is HBr, we say hydrobromic acid. Okay, hydroadded. So that means it is produced from it has an anion, which is basically a non-metal, or more clearly, it doesn't contain oxygen. Okay, if it doesn't contain oxygen, then you do the hydro. We say no O hydro. Okay, so you can remember this it like this: no O is no oxygen, no O hydro. Okay, and you take the root name, which is chlor, and put a ic acid at the ending. Now, if the anion contains is a polyatomic anion, okay, and these polyatomic ions are basically containing oxygens. Okay, so you have to know the polyatomic ion name. So if the polyatomic ion name ends with an "et", make it an ic acid. If it ends with an "ite", then you make it an as acid. Okay, so ic and as. So if you look at these names here, so the polyatomic ion. So right from here, where you can see these oxygens in these acids, like nitrate. So nitrate becomes nitric acid. Nitrite becomes nitrous acid. So sulfate becomes sulfuric acid, and sulfite becomes sulfurous. Ite becomes us. Now for sulfur and phosphorus, you add this extra thing because there's such a common name. IPEC didn't change it. So okay, let's keep it like instead of saying sulfurous acid, we say sulfurous. And that is for phosphorus and sulfur, you will see this change. Okay, but otherwise everything will follow this naming style. Okay, so all these are acids because there's a hydrogen that is ionizable. Now, if it doesn't have a ionizable hydrogen, then it's not an acid. Remember, that means if I have CH4, it is not an acid because even though there's a hydrogen, that is not an ionizable hydrogen, and you do not get an anion, corresponding anion, okay, when dissolved in water. So Arrhenius also defined bases, and he said that bases are ionic compounds that dissociate into metal ions and hydroxide ion when dissolved in water. So all these that you see on the right are bona fide bases. Potassium hydroxide, sodium, lithium, these are group 1. Calcium, magnesium, these are group 2 hydroxides. Aluminum is basically group 3 hydroxide. Okay, now this definition has a problem. What is the problem? That it is aqueous based. Now, we know ammonia, okay? Like if you look at this example of ammonia when dissolved in water produces ammonium hydroxide, which is a base, so, but it doesn't have a hydroxide ion. So how to define, how to explain that NH3 is a base? Or there are other substances that basically do not dissolve in water. You can do those reactions or organic solvents. So how to define them as acid or base? So it was Lowry and Bornstead who basically modified this definition slightly. So the drawbacks of Arrhenius theory are cannot accommodate bases that do not produce OH minus like NH3. Okay, so Lowry and Bornstead gave the definition of acid base to take care of the above drawbacks. So a Lowry-Bornstead acid is a substance that donates H+. That is how it is defined. Instead of saying producing, produce means it actually exists. Donate means it happens in transition, right? As a tension state or as a quick intermediate, but doesn't exist till the end of the reaction. So these are donors. We say acids are H+ donors and bases are H+ acceptors. Now, by that definition, free H+ ion does not exist, and that is one of the problems with Arrhenius definition, because free H+ means a proton, and a free proton cannot exist. So, what Lowry and Bornstead says that this H+ that is produced or donated immediately get accepted by water to produce the hydronium ion. And that is how, the H+ exists as a hydronium ion. And so when you say that H+ ion is produced, what is getting produced is hydronium ion. So accordingly, if you think of HCl dissolving in water, the hydrogen chloride, which is the hydrogen chloride gas basically, gives the proton to water and produces hydronium ion, and itself becomes chloride ion. So if you think of it, that here there's a pair. HCl is acting as an acid, and water is an acceptor of proton, so it's a base. So there's an acid base always. Whenever there's a donor, there must be an acceptor. And in the acidic solution, you will have H3O plus and Cl minus. Now, this is basically the main theme of Lowry and Bornstead definition. So there's a donor and there's an acceptor. Now, all you need to do is to identify, okay, who is donating? So if you are given an equation like this, and I'll give you a question, can you identify the acid? So the acid is basically the HCl because it's donating the H+, And when it is donating the H plus, it is the water that is accepting it. So water is the base. Okay. If you look at ammonia and water, which could not be defined by Arrhenius theory, can now be defined easily because ammonia accepts a proton, so acts like a base, forming the ammonium ion, and you have the OH minus. So ammonia is a base because it is a proton acceptor, and water is a donor because it is donating the proton to ammonia. So water, kind of a very unique solvent. If you look at both these cases, water can act both as an acid and base. This is very unique. And this kind of substances are called amphoteric substances. Okay. Now, the ammonia, if you look at ammonia, after the acceptance of proton, it becomes the ammonium ion. Now this is a reversible sign. So ammonia, does not. So there's always equilibrium between these two states, and we'll learn more about equilibrium in later part of this chapter. That means the reaction in the forward direction is not complete. Okay, so the reverse can also happen because as the product builds up, they can combine to give you the reactant, and eventually a equilibrium is reached. Okay, so we'll learn about equilibrium. But what you can see is that you can also start from the product side. So instead, so you can take ammonium ion, and if you add OH minus, so you'll get back ammonia plus water at equilibrium. So this ammonium, so ammonia is becoming ammonium. Okay, and if the ammonium ion donates the proton to OH minus, then it becomes ammonia. So this ammonia and ammonium ion are related to each other by transfer of one proton. Okay, so they are called the conjugates. Similarly, water and OH minus are conjugates. They're related to one another by H plus ion transfer. Okay, now water has two cases. This is one case of water where it is behaving like an acid. But again, H3O if H3O plus loses a proton, it becomes water. So these two are related. So they are called conjugate pairs. Okay, so if we look at another example here, so according to Lowry-Bornstead theory, every acid-base reaction contains two conjugated acid-base pair because H plus is transferred both in the forward and the reverse direction. Okay, so this is with hydrofluoric acid. So same as ammonia. So if you look at hydrofluoric acid, HF, when you put this in water, HF loses one proton to water, forming the hydronium ion, and it will become a fluoride. If you look at the reversible reaction, so H3O plus can lose a proton to F minus and give you back the HF. So HF and F minus, these are conjugate acid-base pair. So the acid part is HF and the base part is the F minus. Okay, so these are called pairs. Okay, similarly, water and H2O plus are pairs. So when you think of acid-base pair, they're related by transfer of H plus ion in both directions. Okay. So this is like a terminology. Now because the overall reaction of HF with water is reversible, the conjugate base H3O plus can donate H plus. So you can do the reverse here. H3O plus donating a proton to F minus and giving back the HF. Okay, so these are reversible reactions. So in this example, the acid-base pairs are HF, F minus. You write the acid part first, okay, and then the base part. So acid part first and then the base part with a slash. Now solution of ammonia in water. If you think of the solution of ammonia in water, we discussed that previously. So ammonia and ammonium ion are pairs. Similarly, OH and OH water and OH minus ions are conjugate acid-base pair. Now we talked about amphoteric substances. Water is amphoteric substance. We said because water can take a proton and become H3O minus. Water can also, lose a proton or donate a proton and become OH minus. So it can act both as an acid and a base. So that means these are like sponges. Okay, they can, if you add acid, it will absorb the acid. If you add base, it will absorb the base. Even better is a bicarbonic acid. So these are called amphoteric substances. So our blood, keeps the acid level constant by using bicarbonate system. Okay, we have a lot of bicarbonate in our blood, and because if you add a little bit, if there's a slight addition of base or an acid, it immediately absorbs it both ways. Okay, and so doesn't let the acid concentration or the pH to change. Okay, so we learn what pH is. The pH of blood is 7.4, constant, amazingly constant. Okay, now if the slight changes in the blood pH, we can have, really, bothering health consequences. Okay, so and also, shortage of oxygen absorption and all those things happen. So these are, conjugated acid-base pairs. Like these are like, you have to first identify the reactant that loses H plus, and identify the reactant that gains the H plus, and then write the conjugate acid-base pair. Like if you are given an example like this. Okay, so here you can see, first look at them closely. So HBr is become Br minus. So they are related by loss of a proton. So HBr and Br minus are conjugate acid-base pair. The acid is the HBr and the conjugate base is the Br minus. Likewise, if you look at ammonia and ammonium ion, they're related by transfer of H plus. So ammonium ion is formed by acceptance of H plus. And if ammonium ion loses H plus ion, it will give back ammonia. So these are pairs. So the acid part is the ammonium ion, and the base part is the ammonia. Okay, so we write it like this: ammonium / ammonia. Study check 10.3. So HCN is the acid. Now, what is the conjugate? So what is the base? Not the conjugate. What is the base reactant then? Who is accepting the proton? SO4, SO4 2 minus, not SO, SO4 2 minus. Okay, now when HCN loses the proton, what is the conjugate base you get? CN minus. So HCN is the acid part and CN minus the conjugate base. They are conjugate acid base pair. Similarly, if you look at the sulfate, so okay, sulfate SO4 2 minus, it is accepting the proton. So this is the base, and the conjugate acid is the HSO4. So these two are pairs. So you have to look at it closely. Very simple thing, but just look at it closely, and you will see these pairs. Okay, there will always be pairs. Now, strength of acid and bases. We can always use molarity as a strength. Okay, strength of acid is determined by the moles of H3O plus. Not that how much you dissolve, but how much H3O plus, okay, is produced for each mole of the acid. So that's the strength. We might dissolve a lot of acid, but it's not producing a lot of H plus. Okay, then it's weak acid. Okay, like acetic acid. Okay, so only 5% or even less, 1% of the acid is probably going to dissociate to give H plus. So we look for the strength not as to amount of acid you are dissolving, but more as the moles of H3O plus produced. Okay. Similarly, for the base, the strength of base is determined by the moles of OH minus. So strong acid and weak acids. So strong acids are examples of strong electrolytes. So that means they ionize almost completely. Okay. So if you like almost 99.99% gets ionized. So there are 7 strong acids. Okay, so it's better you know their name, because if you know these 6, then the rest are all weak acids, and that is many. So if you just know, now if you see paradiatic, parabromic, okay, so hydroiodic acid, hydrobromic acid, hydroiodic. So these are halogen series. All these halo acids, they are strong acids. And among the oxy acids, sulfuric acid, nitric acid. So common names, okay? Just remember this, 6 names, and the rest we say weak acids. Okay, so these are all the list of weak acids. So you don't need to memorize them. Memorize these 6. If it doesn't fall into these 6, they are weak acid. Now, what is a weak acid then? Weak acid is something that ionizes partially, not fully. Similarly, the strong and weak bases, these are all strong bases. Lithium hydroxide, sodium hydroxide, potassium, and you can see these names are basically group 1 hydroxides. Now, group 2 hydroxides, strontium, calcium, barium, they are, pretty insoluble in water. But whatever dissolves, ionizes completely. So, in a way, because they ionize completely, we say they're strong, but you really cannot get too much concentrated, solution of them because of the solubility issues. Okay, and these are, used as antacids, the group 2 hydroxides, and the rest are weak bases. And mainly, you will see uh, magnesium hydroxide, aluminum hydroxide, the group 2 hydroxides, uh, and sodium carbonate, sodium, bicarbonate, calcium carbonate. These are also weak bases, and we use them as antacids too. Okay, calcium carbonate, Tom's tablet. So that is what it is. Okay. So basically, they have the ability to react to the acids. So that's why. But we being weak, they do not really damage our stomach too much. So it's not advisable to take like HCl or HBr because it will burn your throat when you take it. So, but aluminum hydroxides in uh, or the magnesium hydroxide, milk of magnesia, are very common, antacids. Okay. Now, acid-base equilibrium. So reactants in acid-base equilibrium are not always completely converted to product. Okay, there's a reversibility because a reverse reaction takes place in which product reacts to form the reactant. So as the product builds up, they start to react with themselves, and so that rate, gradually picks up. So that means there are 2 reactions taking place simultaneously, one in the forward direction and another in the reverse direction. So initially when you're starting, okay, initially at the very beginning of the process, so you have all reactants, okay, and the reactant concentration decrease as the reaction goes on and the products are formed, and you can see product is getting formed, okay. But eventually what happens, the rate at which the reactants are decreasing, or the rate at which the products are increasing, gradually changes, and eventually they become equal. Okay. So this is the point of equilibrium. So as the initial reactants are consumed, okay, so the initial forward reaction is faster, very beginning, as you can see from the slope, and it gradually decreases. And the reverse reaction gradually increases because you have more and more of the product, and then they're going to react faster and faster. And eventually the 2 rates become equal. Okay. So as the initial reactants are consumed, products accumulate, and the forward reaction slows down and the reverse reaction increases. This is other way of saying the same thing. And this condition, where the rate of the reverse reaction is equal to the rate of the forward reaction, we call it equilibrium. So equilibrium, remember, is always about rate, not about the amount of product. So if you get this question, never say that equality comes from the amount of the product of the reactant, but it is basically the rate of the reverse reaction is equal to the rate of the forward reaction. The speed is like the highway. If you think of the highway, the cars moving in both directions, right? So if you watch and count the number of cars passing through a given point, okay, it will be the same. Okay, because as the car enters, some are going out. But you know, uh, if the traffic slows down in one way, then the number of cars passing the other lane will be more. But if they are moving in equal rate, okay, then you will not see any change. And same in chemical reaction. So when you are looking at a chemical reaction and you are feeling that it stopped, it didn't stop. So it is basically going in both directions at equal rate. That's why you call dynamic. So equilibrium means the reaction hasn't stopped. Reaction is going on, but at equal rates in both directions. Now, one thing you can see that when equilibrium is attained, okay, um, so it's basically uh, if you are, let's say, investing in something, a product, you are not going to get any more product. Okay, there will be no increase in product anymore. So equilibrium is basically a killer. Uh, so during the World War One, many studies were done how we can shift the equilibrium, okay, by changing different parameters like temperature, pressure. Okay, so when from these studies, last Chetelier, basically summarized all this understanding that they got from the experiments into very simple, sentence that how will the equilibrium shift when your parameters are changed. So Lasseller principle states that when equilibrium is disturbed, the rate of forward and reverse reaction changes to relieve the stress and re-establish equilibrium. What that means that if you put an equilibrium under stress, the equilibrium will shift so as to remove the stress. So if I increase the pressure, it will try to decrease the pressure. Okay. If I increase the number of moles of reactant, it will try to decrease the number of moles of reactant. If I increase the product, it will try to decrease the product. Whichever direction that happens, that will be favored. Now, this you can easily understand with this nice, two tank situations here. There's tank A and tank B, and they're connected. Okay, and this is like our reactions. We can think of the left tank A as the reactant and the right tank B as the product. And there's a reversibility between them. So water can move in both directions. Now, what happens if I add water? That means if I add reactant on the left tank. So this you can answer this in a very common sense way. What happens? So if we add water to one of the tank, what will happen? Water will definitely move to the other tank, right? Till the levels are equal. And this equal levels means equilibrium. So you had equilibrium, to disturb the equilibrium. How? By adding reactant. What happens? The reactant basically moves and becomes product. So it is trying to remove the reactant. So the stress is addition of reactant. It is trying to remove the stress, okay, by removing the reactant and making more product. And this is just a new equilibrium is established. So after some time, when both the levels become equal. Now, if I add product, what happens? If I add water to tank B, water will move into tank A. So the reverse reaction will favor if I add reactant. Okay, so if I add reactant, the forward reaction is getting favored. If I add product, the reverse reaction is getting favored. Now let's say if there's a tap on tank B, okay, and if I open the tank, that's my product. So I am basically draining out the product. What happens to the water? So as B drains out, what happens to A?
Is there flow into tank B?
Yeah. So more and more of the reactant will try to make product. Okay, and so eventually, you know, all the A will run into tank B. That means all the reactant will become product as you drain out the product, and that is utilized in the industry. You know, very frequently they try to take out the product, so it has to drive the equilibrium in the forward direction continuously. Okay, so this is a very easy way of understanding. So this is a very natural thing, not that they discovered something new. Nature does it all the time, and that is, I think, basic thing in nature. Always, tries to remove a stress that you are putting it to, and reestablish equilibrium. So everything in nature is in equilibrium. Okay, if you think of the earth moving around the sun, it's in equilibrium. If you disturb anywhere, okay, things will change to adjust to that change, and it will reestablish a new equilibrium. Okay, so the effect of concentration changes on equilibrium. So if you think of this way, that this is a good example here, HF plus water. So try to form the analogy with the tank. Okay, so if I add HF into the reaction, what happens? Which direction will it move? It's a reactant, right? It will try to decrease the reactant. So it will move in the forward direction towards the right. Now, what if I add F minus?
To the left.
That means it will move in the reverse direction, forming more of the HF. What if I add H3O plus, which is an acid?
Will also move to the left.
Right.
To the H2.
So if I add acid, it will form more of the undissociated HF. If I add salt, now we cannot add H minus like that. We have to add like a salt, like sodium chloride. Okay, so it will contain F minus, and that will drive the reaction in the reverse direction. Okay, so if more HF is added to the equilibrium mixture, which increases the concentration of HF, the system relieves stress by increasing the rate of the forward reaction. So according to last year principles, adding more reactant causes the system to shift in the direction of the product. That's a general phenomenon. Okay. And if I remove HF, then more and more reactant product will move towards formation of HF. That means the reverse direction. Okay. If I add more F minus, which is like is in the form of salt, like sodium chloride, the reaction will move towards the left. So this is a very nice concept because, summarizing this into very simple, idea, but the things are more complex than that. But for our purpose, the simple idea kind of helps us to dictate how the equilibrium is going to sit without going into any mathematical details. Okay. Now, so this is summarized in this table. Okay. The whole thing. And think of the water tank if you ever get confused. Okay. Because we have seen this all the time. Okay. Now, so we know water is amphoteric. That means it can behave both as an acid and a base. So if you think of pure water, in that, one molecule can act as an acid and another molecule can act as a base. And that is exactly what you see. Okay. So if you think of pure water, in that you have one water molecule acting as acid, another one as a base. So water itself will have some amount of hydronium ion and some amount of OH minus ion, equal amount. Okay, equal amount, 1:1, all the time, and this is in equilibrium. So water itself acting as an acid base forming this. So this is called the ionization of water. Now, the ionic product, which is basically defined as the concentration of H3O plus multiplied by the concentration of OH minus, has a constant value. Okay. At 25 degrees centigrade, this is 1.010 to the minus 14. And under this condition, because OH minus and H3O plus are all equal, the concentration of H3O plus in water is equal to 1.010 to the power minus 7 molar. So that is the situation. Now water we call is neutral. Okay, so neutral, even under neutral conditions, we have 1.0 10 to the minus 7 molar of H3O plus and the equal amount of OH minus. That's why it's neutral. Okay. The H3O plus and OH minus are in equal concentrations. Now, if we add something, and if the H3O plus increases, then we call it acidic. If the concentration of OH minus increases, we call it basic. So for any aqueous solution that is neutral, acidic or basic, this product is always going to be constant, because this comes from thermodynamic considerations. So you don't need to just know that it is going to be constant. Okay, the multiplication, so product means multiplication. So H3O plus, we multiply H3O plus and OH minus is always going to be constant, because that comes from another constant, what you call the equilibrium constant. Okay. So because this is equilibrium of water, and if you establish the equilibrium, if you calculate what the equilibrium constant is, it will come up with this value. Now, what that means that we say Kw is a constant. If I increase H3O plus, OH minus must go down. If I increase OH minus, H3O plus must go down. Okay. But the total product, total multiplication, if you do a multiplication, they are always going to be 10 to the power minus 14. Now, because of this equation, we can now calculate either OH minus or H3O plus given the other. So you can look at some examples here. There is something like this. So this is a neutral situation. You have the equal amount of H3O plus. So if I add H3O plus, if the H3O plus increases, then OH minus must go down. How much? So that the product is still 10 to the power minus 14. Okay. So you can basically calculate what is the final concentration of H3O plus. Okay. So calculating the H3O plus of a solution. A vinegar solution has a OH minus concentration of 5.0 10 to the minus 12. What is the H3O plus concentration? Now square bracket means concentration. Okay. In the vinegar, so is the solution acidic, basic, or neutral? So this is what is given to you. Okay, and you need to know this one. But you also know this, that Kw is 1.0 10 to the power minus 14. Okay. So you can basically say that H3O plus equal to 1.0 10 to the power minus 14 divided by concentration of OH minus. So if you substitute this, each of these values here, then H3O plus comes out to be 2.0 10 to the power minus 3. Now, OH minus concentration, if you look here, was 5.0 10 to the power minus 12. And the H3O plus is 2.0 10 to the power minus 3. Which one is greater among these two? 10 to the power minus 3 or 10 to the power minus 12?
10 to minus 3, no?
Yes, that's greater. So negative values, the smaller the negative, the better. The greater it is. So 10 to the minus 3, that's greater. And so the H3O plus concentration is higher. So the solution is going to be acidic. Okay. Now, what I want you to do is to do this, step 3 in your calculator, and see that you are getting this exact same answer. Don't forget to use parentheses. And then you will do the study check 10.6. So are you all getting 2.0 10 to the power minus 3?
Yes.
Okay. I just wanted to check that you are using the calculator properly, because a lot of mistakes come from the use of calculator.
Oh.
Okay, so just be careful, use parentheses when you are dividing, okay? Multiple factors. Okay, now let's do 10.6. So what is the H3O plus concentration of an ammonia cleaning solution It's contains ammonia basically. With the OH minus 4.0 10 to the minus 4. So the formula, remember, Kw equal to H3O plus multiplied by OH minus. So you have to rearrange to get H3O plus. So H3O plus will be Kw by OH minus. So put the value of Kw and put the value of OH minus. 2.5 10 to the minus 11. And I can see this correct because if you multiply them back, you can get 10 to the power 14. So that is another check that you can do. So if you multiply them back, you should see 10 to the power minus 14. Okay. So minus 11 and minus 4 is minus 15, 10 to the power, and then 2.5 into 4 is 10. So that means 10 to the power minus 14. So it looks correct. All right. Now, this is fine. We could have kept it like that as acid strength or H3O plus and OH minus concentration, but a more convenient way of expressing H3O plus and OH minus is basically as the log, because these are to the power. Log is basically the reverse of power. Okay, so let me get my iPad. It's a reverse of exponent. You can say that y equal to a to the power x. Okay, so it's like y is output, okay, and x is the input. If you think of it this way, that if there's a machine, okay, x is the input. We always put in x, and y comes out like an output of that. So now if you have a reverse machine, okay, where you put in y and you get back x. So it's like, so you can think of like, this is the first machine. You're putting in x and you're getting y. And now you have inverse machine where you put in x and you're getting back. You're basically putting in y and getting back x. You can think of it this way, that our exponent is a machine which is normal machine, right? So you have flour, and if you put the flour inside, you are getting back tortillas. Flour tortillas, let's say. Okay, now if you want to do the reverse, that means you put in tortillas and getting back flour. That's the log. So simply this word log means reverse of power. That means if I put in y, I'll get back x. So if I put in like log of 10 to the power x, I'll get back x. So the answer is x. It's just the inverse function. That's all. Okay. So it has always a base. Is the base 10 we are going to use. Okay. That means if it is a base 2, then we can say that 2 to the power x log 2, log of 2 to the power x with the base 2 will always give back x. That means you're getting back your input. Okay. That means if I have, log of 10 to the power x to the base 10, I am getting back x. So if I have log of 10 to the power, minus 3, I will get back minus 3. So it just reduces into a simple number. Okay, that's the advantage. So you can see that we define pH as the minus log of concentration of hydrogen ion. Why minus? Because the power is negative, so we'll always get the log as a negative value, just to take care of the negative, so that we always get a positive sign. So we saw that neutral water, has a hydrogen ion concentration of 10 to the power minus 7. So if I write it like pH equal to minus log of concentration of H3O plus, which is minus log of concentration of 10 to the minus 7, I'll get back 7. So this is basically the log. Okay, how it is defined, and this is how log works. Now, these are some of the rules for log. Okay, so log of a to the power x to the base A is always X. And log of A multiplied by B is log A plus log B. So multiplication gets added. So remember, powers get added when you multiply. Okay. And powers when you divide, you subtract, right? With the same base, it's same idea. So mathematically you can get there. Okay. So log of A multiplied by B equal to log A plus log B, and log of A by B equal to log A minus log B. Okay. Now you can use a calculator to get the log, but these are simple math that if you know, uh, becomes much easier. Uh, you know, or you can check your errors. Now, if you look at the next example there, I just did a log. Let's say the hydronium ion concentration is 1.508, 10 to the power minus 8. Okay. So I can do, log, I can look at it as log A multiplied by B. I can write it as log 1.508 plus log of 10 to the power minus 8. Now 10 to the power minus 8, when you take the log, it becomes minus 8. Okay. And the other part is log 1.508. If you look in the calculator, let's check how much do you get. So do this. Okay. Now, depending on a calculator, you might have to put the log first, then the number. In some calculators, you have to put the number first, then log. So let's see which way your calculator works. So usually the log parenthesis and the number and close the parenthesis and it's equal to will always work. Does work all the time, most of the time. So let's take this and let me see that you are getting that number that I have there. 1.508. Take a log. 178401. Now, if you look at the last line here, if you look at the last line, so this basically is subtraction, right? So or addition, you can say that you are adding two numbers here. So addition subtraction has the same rule of significant figure. Okay, so this 8 is a constant number. If you look at 10 to the power 8, this is a constant number. There is no change there. And in exponent, the significant figures are always determined by the real part. Okay, because the exponent part, like 10 to the power 4, is 10,000. There shouldn't be any error. It's like a count. 1 by 10 to the power 8, which is 10 to the minus 8, is a constant number. So when you are adding these two numbers, this is the only part that will have significant figures. And the significant figure will be same as that number 1.508. Okay, so the number of significant figure will always be 4 here. Okay, and you are adding it. So 3 decimal place you are adding. So you must stick to 3 decimal place. That's why, so when you are going from concentration to pH, the concentration has in a 4 significant figure, you must carry 4 decimal places here. And that comes from this rule. Okay. So number of significant figure in the concentration of H2 plus will be equal to the number of decimal places. Okay. So just remember it like that, and this is how you can explain it. So this is the concentration of, so if you look at this in this box here, so this is basically the summary. When you go from H2 plus and to pH, the number of sigfig is equal to the number of decimal places. If you do the reverse, then the number of decimal places will be the number of sigfig. Okay. So that's how we decide on how many decimal places in the pH you should have, because you get a whole phase number, and that's because of this mathematics of the log, nothing to do with chemistry. Okay. Just remember it like that. So this is the value, this is the expression of pH. pH equal to minus log of concentration of H3O plus. And if you take the log of 10 to the power minus 7, it will become 7. Okay? When you do the pH, pH becomes 7. So neutral solution has a pH of 7. And if you think of acidic solution, that means 10 to the minus 3 is acidic. If you take a pH of that, it becomes 3. That means anything less than 7, you see, is acidic. And anything greater than 7 is basic. Okay. So just keep that concept. Now, in the lab, we have this, we can use a pH meter, which gives it actually a very accurate reading of the pH. We can use strips. Now, strips are more like broad range, okay? But some are, you can get pH paper that can be very close. Now you can see this pH paper changes color from 0 to all the way to 14 or 11 here. But the color changes between 1 and 2 is very hard to pick up. You can broadly say it is 1 or 2 or 3. pH meter is more accurate. And you can see the color changes with indicators here. So you can use this as a means of determining the acid concentration, the pH of the solution. Okay. Now, the guide to calculating the pH of an aqueous solution, okay, state the given and needed quantities, enter the H3O plus into the pH equation, take log by pressing the log key and change the sign. So do not forget to change the sign. Okay. And another thing is that when you do the concentration has a negative power. During this problem, calculating the pH from H3O plus, if a solution of aspirin has a H3O plus concentration of 1.710 to the minus 3, what is the pH of the solution? So this problem actually walks you through the calculator. Now, if you already know how to do it, that's fine. Okay, just give me the pH in the correct number of CP. So here you can see that these two significant figure. So your answer must be in 2 decimal places when you give the pH. So you all got 2.76955 the display, right?
Yes.
Okay, so now you have to practice it several times. Okay, because I know many careless mistakes happen from here. Okay, now you have to keep to 2 decimal places. So you have to round it. So when you round it, this becomes 2.77. Okay. Why? Because 2 significant figure is what you have. Okay, try this one. 10.8. And then you will do the reverse. pH to concentration.
11.38.
Yep, that's correct. That's very good. So the opposite of, you go from pH to H2 plus, the formula is 10 to the power minus pH. You just raise the whole thing to the power of 10. Okay, so just reverse. You're reversing the calculation. So 10 to the power minus pH. So like if you look at this example here, the pH of a sample of water, let's say solution, is 8.5. So what is the H3O plus concentration? Okay, so you just put 10 to the power minus 8.5 and hit equal to, but you cannot leave it like that. So you have to write in the proper scientific notation, same as doing inverse law. So you can also use inverse law. So it's 8.25. There's a typo here. And this is 2 decimal place. So answer must be in 2 CP. Now, depending on the setting of a calculator, you might get 0.0000. And yeah, so you can set your calculator to scientific notation. Okay? So if you go to like functions, so if you hit second, so if you are using a Texas Instrument 2, so just hit the blue button second, and beside that there's a DRG, and on the top you can see SCI and engineering.
Oh, I got it, Professor.
Yeah, so you can change the format.
Okay.
So it becomes easier if you change to. So there are three, uh, you know, scientific unit, and so you have to use the arrow basically to move from one to the other. Flow means you get the all decimal places, and if it is SCI, it will always try to give you exponent. You can try and see which is more convenient for you. I'm getting 5.6234 10 to the minus 9. So I changed mine to SCI. You can all do that, okay, when you do this kind of calculations. Because otherwise, you might have so many zeros in front, it's very easy to make mistakes. And oftentimes, your calculator may not have enough, place to contain all the zeros and the numbers. It can overflow. So try 10.9, okay? So this time you are doing 10 to the power minus 4.5.
4.5, yes. So I got 3.1622776.
Right. So, but you have to keep to one significant figure because there's one decimal place.
So would it be 3.2?
No, just 3.
Just 3?
3 multiplied by 10 to the minus 5. So when you give concentration, there must be a molar term. pH is unitless, but when you convert that to concentration, it must be stated in molar. Unit must be there. Now, if you look at this chart here, so this is what you get. So if the STO plus is 10 to the power 0, pH is 0. Okay, because you take a log, it's a 0. So log 1 is 0. Okay. And the concentration of OH minus is 10 to the minus 14. So if you multiply STO plus and OH minus, these two columns, okay, first column and third column, it will always be 10 to the minus 14. The powers add up, right? So if you look at this, that the STO plus is decreasing downward, okay, as you go down, while the pH is increasing. So they're opposite, okay? So please remember this. But that means pH 7 is neutral. Less than pH 7, we say it is acidic. Greater than pH 7, so that means pH 8, pH 9, these are all basic. And something very easy to make mistake, okay? Remember this, the pH basically goes in opposite direction. If you increase the STO plus, pH will decrease because there's negative sign, that's why. Now, if you look at the OH minus, when the STO plus goes down, the OH minus goes up. Okay, so, and the product is always 10 to the power minus 14. And this is a nice chart to look at. Okay, so if you take a POH, so if you write the POH on the next column here, okay, so that means POH is 14, then 13, 12. So if you add pH and POH, they're always equal to 14. So given pH, we can always calculate pOH. Okay. 14 minus pH is a pOH. I'll quickly share my iPad with you. See, these are what you see in the box is basically the basic formulas. And that is all you need to know. Okay, STO plus multiplied by OH minus is 10 to the minus 14. pH equal to minus log of concentration by STO plus. pOH, similar to pH, is minus log of OH minus. And pH plus pOH is always equal to 14. And you can see why. If you take log on both sides, this becomes pH and pOH, and this is equal to 14. That's why. And this is like a Gantt chart. Okay, so given something like this, like I will give you a table. Okay. So the black ones is what is given to you. You can try this. So let's say in the first row, you have SCO plus 3.80 10 to the minus 8 molar. Can you fill up the rest? Concentration of OH minus, pH, pOH, and acidic or basic. So this is nice practice. So consider that 3.80 10 to the minus 8 is given to you. Don't look at the answers now. Try to do it yourself. Calculate the OH minus, calculate the pH, calculate the pOH, and say acidic or basic. So the column headings is what you are trying to do. So don't look at the answers right now. Just do it yourself, your way, and then you can look at the answer whether you got it correct or not. And then so you have the pH. You can now calculate the pOH. 14 minus pH is the pOH, and then try to calculate the concentration of OH minus, and try to say whether this is acidic or basic. After you do that, you try the second row, and then the third row.
It's
In
10.
the second column is the concentration of OH minus.
That's minus. Oh, okay. It looks like a dot. Okay.
So you can do it many different ways. Like you can do it kW by concentration of OH minus. That's I did for the first row. Okay, or you can decide to do 10 to the power minus POH.
Mm.
So there was little differences in the answer. Like if you see in the third row, I did it 10 to the power minus POH. So I just showed different ways of getting to the same answer. Okay, so reactions of acid and bases. So all acids, reacts with metal. Now, when you think of metals, reactive metals. So reactive metals that are more reactive than hydrogen. In the if you look at the activity series, okay, in the single displacement redox reactions, we have the activity series. So activity series means we can put the metals in order of the activity. So those metals that are above hydrogen in that activity series, they can react with acids to liberate hydrogen gas. That's the reaction. The acids have more reactions than the bases. Okay, so this is one important reaction. And acids, they react with carbonates and bicarbonates to liberate carbon dioxide gas. And these are kind of, you can use it as a test. Carbon dioxide comes out, you can test for carbon dioxide. And acids and hydroxides, they can neutralize one another. Like H plus and OH minus, they can come together to form water, H2O. Okay, and that's called neutralization reaction. So neutralization is reaction between acid and base to produce water and salt. So if we write strong acid, strong base, and salt as ion, then we'll see that H plus reacts with OH minus, and leaving the ion sodium plus and Cl minus in solution, which is basically the ionic reactions. So if you basically write the ionic reactions for acid and base, that is what you'll get. So we already know what ionic reactions are. Okay. So acid-base titration is a technique, uh, is a stoichiometric technique. So in which the molarity of an unknown strength of an acid or base is determined using the known strength of one. Okay, utilizing the neutralization point. So you have to know where the reaction is ending. So the end point. So you know the end point by adding what you call a indicator. So in this, the classic indicator that we use is phenolphthalein. Okay, phenolphthalein is colorless in acid, and you take it in a, so you take the acid in a conical flask like this. Okay, add the indicator, it's still colorless, and in the burette you have the base, and you keep adding the base, and it's continuously neutralizing the acid, and when it completely neutralizes, and then you add one extra drop, the whole solution becomes alkaline, and it becomes permanently pink, and that is where it stops. Okay, so this technique is called titration. Now, when you are adding you can read out from the burette how much volume of base you have added. You know how much volume of acid you have taken. Let's say that if you know the strength of the base, you can figure out the strength of the acid using stoichiometric calculations. So here is a simple stoichiometric calculations. So stoichiometric calculation is always mole to mole, remember. Okay. So a 25 milliliter sample of HCl, so this is the volume of HCl, the acid you have taken, is placed in a flask with a few drops of indicator. and you are titrating with sodium hydroxide. So if 32.6 milliliter of 0.185 molar sodium hydroxide solution is needed to reach the endpoint, what is the molarity of the HCl solution? So you know the volume of sodium hydroxide required. You know the molarity of the sodium hydroxide. So you know how many moles of sodium hydroxide you have added. Now this is the stoichiometry of the reaction. Okay, you have to always write this balanced chemical equation. Now in this case is 1:1. So 1 mole of sodium hydroxide will react with 1 mole of HCl. Okay. So at endpoint, they are going to be of equal molarity, equal moles. So figure out from the volume of sodium hydroxide and the strength, the molarity, the number of moles of sodium hydroxide. So you convert the milliliter to liter, and from liter of sodium hydroxide, you go to moles of sodium hydroxide. Now the stoichiometry, this is the pink step. So you know 1 mole of sodium hydroxide is equal to 1 mole of HCl. So you can figure out the moles of HCl. Now once you get the moles of HCl, you can figure out the molarity because you divide by the volume, and that's the molarity of HCl. Very straightforward kind of problem. Same stoichiometry. Only thing is that here you are using the molarity. We did the molarity before. Remember when you did the solution, how to calculate moles? This is the same problem. We actually did exactly this problem, this kind of problem in that chapter. We're just seeing it again. Okay. So you are starting with 25. So these are your conversion factors. Remember, you need a conversion factor here. Where you're going to convert the milliliter to liter. You need another conversion here for molarity. Okay, molarity conversion factor. So you know the molarity of sodium hydroxide. So that goes here. And every time that you're doing, you are going to follow the unit. Okay, so if you place them, this is how these are. So this is color coded. So you exactly know which factor means what. So you are going from milliliter to liter. You're canceling out the milliliter. Okay. Then from liter to moles, your liter and liter cancels out. Okay. And then mole of sodium hydroxide to mole of HCl. So your mole of NaOH cancels out. So you are getting 0.00603 mole of HCl. Now you know the volume you have taken. You have taken 25 milliliter, which is 0.0250 liter. You divide this two, and that is equal to 0.241 molar HCl solution. Okay, now, so if you understood this, can you do the next problem? What is the molarity of an HCl solution if 28.6 milliliter of 0.175 molar sodium hydroxide solution is needed to neutralize 25 milliliter sample of HCl? So you have to do it the same way.
Okay.
So always start with a balanced chemical equation, which is same as, which is basically same as the previous one. So that's the equation over there. NaOH plus HCl to give water plus NaCl, you have to use the same equation.
Okay.
Okay. And then do it the same way.
Okay.
So everybody's try study check 10.12. Remember, you are going from, this is your solution map. You are going to use the same solution map here. Liter of sodium hydroxide to liter of sodium hydroxide. From their moles of sodium hydroxide, from their moles of HCl, and then, so you basically stop here. And then in the next step, you divide the mole by the liter of HCl, and that is a molarity. Everybody do it, okay?
Everybody. 1 liter. Okay, so molarity, give you step. I don't have enough paper. 1 liter. Okay, 0. Point. Oh, let me turn my microphone
And you can see the steps basically on the side written. So these are the steps 1, 2, 3, 4 that you need to follow. 0.200 molar.
Okay.
So in the exam, never do it C1 V1 equal to C2 V2. Unless until it is normality, it will not work. Okay, or even if you get the right answer, that will be for wrong reason. Okay, so technically it will be 0, even with the wrong answer, even with the right answer. Okay, if in a free response, you have to go from moles to moles, showing the stoichiometry. Okay, unless until you convert the molarity to normality, C1 V1 equal to C2 V2 is not acceptable.
Okay.
Okay, so you might get the right answer, but that's for wrong reason. C1 V1 equal to C2 V2 is only applicable for dilutions. We'll see what dilution is. And we basically saw that in the previous chapter, what dilution is. But the important thing is, if you convert to normality, yes. Otherwise, not. Because if I give you sulfuric acid, this formula is not going to work unless until you convert the molarity to normality. 200 molar HCl. Okay, now if I give a sulfuric acid, again, C1 V1 equal to C2 V2 is not going to work.
No.
Now, buffers, very, very important. So those of you who want to work in biochemistry or microbiology, you live with buffers, okay? So your experiments cannot be done, your cells cannot survive without a buffer. So what is a buffer? The buffer is a solution that can maintain its pH even after adding small amounts of acid or base. They're resistant to change in pH. And that is very important for cells, especially cells and enzymes, because they are fine-tuned to a particular pH. Okay? Our body system likes certain pH and does not like certain pH. And so are the enzymes or the cells that you get from them. Okay? So the buffers are there for, so if you are culturing cell and you are probably adding zillions of things there to make a media, so your pH is going to change, but you want to keep it exactly 7.4, and that is what the cell likes. And the only way you can do that is keep it buffered by adding a suitable buffer that can maintain that particular pH, even if you are adding a little bit of other things there. Okay, so what are buffers? So buffers are basically, now this is the important word here. Buffers are mixtures of weak acid and its corresponding salt. Weak is the strong word there. Weak, it has to be weak because then the reaction is reversible. It can go both directions. If it's not reversible, if it's strong acid, then the buffer, it will not have any buffering action. It will not have the buffering capacity. It has to be weak acid and the corresponding salt. That means a weak acid, name a weak acid like acetic acid. So acetic acid and this salt, that means acetate. So you can take weak acid and this corresponding salt, or a weak base and this corresponding salt. So what that means, if I take acetic acid, which is a weak acid, like the example here, and then the salt is the sodium acetate, the corresponding salt of this acid, these two will make a buffer system. And you can explain this buffer action by thinking about Last-Life principle. So because there's reversible, now I didn't get a suitable reversible sign, so I use this sign. So this is reversibility. So acetic acid dissociates into H plus and CH3CO minus, which is the acetate ion. So if I add H plus, if I add a product, what happens? The reaction will move in the opposite direction, right? In the reverse direction. That means H plus will combine with CH3CO minus to give back CH3COH. That means your H plus is getting removed because of the buffer. So it has to have the salt, CH3CO minus, in order to be able to do that. And so you can explain that using last order principle. Now, what happens if I add a base? If I add a base, OH minus, okay, the base OH minus will react with this acid, CH3COH. That means this, so the base is getting removed, the CH3COH is getting removed, and the reaction is going to move towards the right. So basically, it will try to produce more of the H plus ions, okay, because you are producing CH3COH, is going to increase, okay. Okay, now hold on. So if you add a OH minus, so OH minus will react with the H plus to form water, and you will produce CH3CO minus. So that means you need this acid, weak acid, to react with the base, and you need this salt to react with the acid. And as it's sponging out any excess H plus and OH minus that you're adding. And that is buffer action. Okay. Now, if you look here, so this is what you started with. Let's say equal amount of acid and the salt, and this is acetic acid. Okay. So if you add acid, the acid will react with this salt here. So the salt will decrease, your acid will increase. And what the overall thing, what it is doing, whatever additional H3O plus you added will get removed. So there will be no change in pH. And if you add a base, the base will react with this acid, okay? And that is decreasing, your salt is increasing, but in the process, what is happening? The additional OH minus that you added is getting removed. So the concentration of the H plus, that means the pH, is maintained. So remember the keywords. Always it needs to be weak acid or weak base. So if you try to do HCl and sodium chloride, it will never make a buffer. Or nitric acid and sodium nitrate will never make a buffer. Okay. Acetic acid and sodium acetate will form a buffer. Citric acid and sodium citrate will form a buffer. So when you form the buffer with acetic acid and sodium acetate, we call it the acetate buffer. Citric acid and sodium acetate will form the citrate buffer. There are numerous buffers available in the market, depending on at what pH you want to work. Or, when I say market, I'm wrong, you have to make your own buffer. But those salts and acids are available, okay, in the market. So you can buy and mix them together. But you have to make your own buffer in the lab. Okay. So this is buffer action. So all you need from here is what is buffer, and that weak acid or weak base and its corresponding salts make a buffer. And strong acids do not make a buffer. You have to remember this keywords here. Okay. So I think we are at the end of this chapter now.